Okay, start recording. Let us now share the screen. We are grading the exam. It's going okay. I think most people did well. We are also, as I mentioned in the announcements, I'm going to send out how I calculated your grades so far, probably by Thursday. In this way, you can go and do it and find out how you're doing. Because last spring I did it all on my own. It took a long time, emailing people their grades one by one. It was a bit of a time consuming process, but I found out some students didn't really need to know that because they were doing well enough that they're fine with it. Okay. Let's share screens and let's continue talking about heat effects. We'll briefly mention where we stopped and where we're going. Now, I trust that you guys can do adiabatic reactions because they're rather simple. And your homework, or at least your past exam and on the exam, you all did rather well with that. So let's okay. So previously we studied adiabatic reactions. And these were very simple. So what we ended up with is the energy balance having this form. I'll do the y's to
Sorry, I had a quick question. So for our
yes.
last quiz, would it be next Thursday then?
Your last quiz?
Yes.
On the 21st. When is that? The last day of when is the last day of class? Is it 20th?
Technically the 21st.
Is it 21st? I thought it was 20th because it's next Tuesday. Yeah, I think I made a mistake on the syllabus.
Oh wait, oh yeah, 20th. Sorry. Okay,
Yeah.
so next Tuesday. Okay.
Yeah. Your last quiz is on the 20th. The last day. It's like a very nice goodbye gift for now. So yeah, so this is what we sort of computed, and we can do the same. If it's a batch reactor, we can write it as this. Of course, we made some simplifications. This is Fi naught. Right, so we made some simplifications with the heat of reaction. If we can assume that it's temperature independent, we can write it as, so this is temp independent. We can write it as the delta H at reference temperature. And that's usually what we end up doing. So you can keep that in mind. So that's where we were. And we talked about how you can solve problems using these when you have energy balances. So if you have a PFR, if you write your mole balance for a PFR, so if we think about how you solve problems, so if you have a mole balance for a PFR, which let's say in terms of XA, it's something like this. Okay, something like this. Now, say that your minus RA is just KCA, sample. what happens is K is a function of temperature. So your K is going to be some K1 at some temperature 1 exponential of, say, E over R, 1 over T, 1 minus 1 over T. And that's times CA naught, 1 minus XA. So in this particular case, you find that when you're going to integrate that mole balance, you are going to have to plug in what the temperature is, which is in this case a function of XA. So this is how you would solve. It's a similar process for a batch reactor, right? For adiabatic batch. For adiabatic CSTR, because it's algebraic, so it's much simpler. So for CSTR adiabatic, remember that the reactor operates at the temperature of the reactor is the temperature of the effluent. So the temperature at which the reaction occurs is the same temperature as which the product leave the reactor. So if you take your mole balance, over minus RA, for example, that minus RA is evaluated at XA, and the temperature that the minus RA is the temperature at the exit. So if you basically pairing up this reaction, becomes rather simple to just calculate what if you're given conversion, you can calculate temperature, you can calculate K, then you can calculate minus RA, and you can calculate volume. So you can go in this direction. Going the other way of given temperature and calculating, you can calculate XA, and XA you can calculate RA, and you can also calculate, so from temperature you can calculate XA. In this case, you don't even need to know the reactor volume, right? If you're given temperature in, temperature out, temperature in, and you're given delta H of reaction and everything else, you can calculate your conversion, right? And then using that, you can go and calculate the volume of the reactor that would give you that conversion. So it's very straightforward there. So that's where we had stopped. We did some work looking at equilibrium conversion for reactor staging. So we did some work there. Oh, did I lose? Oops. Hold on, I got knocked out of. Did I get accidentally? Oh no, I didn't. I thought I got accidentally removed from Zoom. Oh, never mind. My laptop is screaming. It's screaming. It's in pain. Okay, so now where are we going? The next stop is it's a very exciting topic, is looking at CSTRs with heat exchange. So we're gonna look at today. We're gonna look at CSTRs with heat exchange, and we're also gonna look at PFRs with heat exchange, as in either a heat exchanger or a coil, or these types of things, where the Q term in the energy balance is not zero. Okay, so for adiabatic, Q is 0. And then we looked at isothermal, where the change in temperature between the feed and the temperature of the reactor is 0, right? So now we're looking at an example where Q is not 0. And also the temperature from the inlet to the outlet is also not 0. The difference is not 0. So let's look at that. And this is where some very exciting things start happening for a PFR, for a CSTR. So we can rewrite the energy balance just for completion. Okay. So we write it as this for simplicity. This is delta. Okay. Now, we had done that a little bit before. So that term Q, let's start looking at it. This is a heat flux, which is equal to the heat transfer times, heat transfer coefficient times the temperature difference, which is then temperature of a coolant minus T, like we call it a coolant by convention, but it could also be a heating for endothermic reaction. It could be a heating fluid instead of coolant. So now that Q is a heat flux per area, and U is the overall heat transfer coefficient that one can calculate from the Nusselt number in your transport classes and fluids. Okay, and this is in per degree Celsius or per degrees Kelvin. Okay, so these are the units of that. So effectively, the heat you add is going to be Q times an area times delta T, right? So it's U, it's going to be UA delta T. So it's going to be did I do this right? Or did I make a mistake? Never mind. Let's erase that. Does it make sense? So the Q you have is a QA delta T. Now for the case of in the class, what we're going to do is instead of, we're going to assume for CSTRs that the cooling liquid has a very high flow rate. So such that the temperature between the entering cooling fluid and the exit cooling fluid is the same. So if we draw out a reactor, this is a CSTR with inlet and exit.
Dr. Denard?
Yes.
Where's the time component coming in from?
Time?
Yeah, when you're multiplying U by just temperature, where do you get it in per hour for Q?
Well, it's so. Yeah, give me a second here. Let me take a look. I wrote this, but then I had a bit of trouble. Wait a minute. So Q, large Q here is per time, right? Because it's flow rate, it's heat rate, right? This is per time, right? This is mole per time. Does that answer your question?
Yeah, but small q, don't you have it joules per area hour?
Yes.
So if you're multiplying U with temperature change, where's the time coming from?
Oh, I see. I made a mistake because there I missed this here. That's what I did. Yeah.
Okay.
That's where the time comes from. Yeah. I missed that out. Okay. Yeah, thanks for checking that. All right. So if you have a reactor where you have, this is your entrance to your CSTR, and you have some conversion at temperature, and you have a jacket around your CSTR. So this is a jacket. Put it in black. Okay. This is a jacket around this tank. So what we're going to assume in this course, at least for CSTR, is that the temperature of the coolant at 1 and temperature of the coolant at 2 is the same because the molar flow or the mass flow is very, very, very large. So the temperature change is not very, it's not significant. So when we do that, we can write the term Q as equal to UA time temperature of coolant minus T. So that's what the term Q is going to be. So you see that it's heat being removed from an exothermic reaction, for example, and in this case, if you call it T8, which is heating temperature, it would be positive for giving heat to an endothermic reaction. But I use TC as a convention because we mostly deal with exothermic reactions instead of trying to flip-flop between them. So you can plug in Q in the energy balance. You can rewrite the energy balance. And that is, and you can do some switching things around. Oops. Sometimes you'll see a little H under A. That's really not, that's just convention. This just means area of heat transfer, but we can just leave it at A.
Dr. Denard, we can't hear you.
Can you hear me now?
Yes.
Okay. Well, I hope this doesn't keep happening because this is a bad sign. Because this happened before, like a week ago. It's not good. Okay, what I'm gonna do, I'm going to keep an eye on it and fix it if it happens again. So what was I saying? I don't know where I was, but let's see. That was a minute and a half ago. All right. Now, what we're saying is that we can write the energy balance and split it into two terms. So we have an R of T term or G of T term, which is a heat. This is enthalpy change upon reaction. And there is a term that is R of T.
Can you share your screen?
See, this is going really badly. All right, there we go. That's good. Now we hopefully that's the last of that. So yes, so we can have a G of T term, when we look at the energy balance, we can split it into a term on the left. This is the enthalpy change on reaction. And there's a term on the right, which is, we can call it a heat remove term, because this is the heat that you need to either add or remove to get your temperature to the temperature of the reaction. So from T0 to T. And there's the term that you're adding heat from, let's say, a coil heat exchanger of the CSTR. So you have those two terms. The one thing you can do is this R of T term, you can rearrange it to be a straight line, where you can rearrange that term and write it R of T is equal to UA plus sum of the flow rates times T minus UA times coolant temperature plus sum of flow rates times T0. So you can rewrite it, you can just rearrange it this way. So now if this is a straight line, your slope is going to be this, and your intercept is going to be this term. So this leads us to the question of how do we solve problems with CSTRs that involve energy balances? The one thing to keep in mind, very important, is that this is where your mole balance is. So this is your mole balance, right? It's actually in the energy balance equation, right? Because to calculate XA, you need to solve your mole balance. So that is where your mole balance comes in. So that's what you should keep in mind. So how do you solve those problems? We're not gonna do them, they're mostly gonna be done graphically. That is how we're going to do them, is graphically. So the way you solve the problem, say you have a rate, say you have a certain equation and the rate is minus RA, and that's in the book, actually, you can check this out, is this, right? This is your rate equation for some kind of A goes to products. And there's heat effects. So the way you solve this is you pick a temperature, you evaluate K, and other constants. Another constant would be equilibrium K, right? Or this one is Ka. So you can evaluate all these constants at that temperature you picked. You can solve the design equation. You can solve mole balance also. And then find XA, right? With the mole balance. You can calculate G of T, which is, if you remember, that's equal to that, right? That's a G of T. And you can plot G of T versus T. So this is the first thing you would do. This is plotting your G of T curve. And you can also plot your R of T line from this equation up here, right? Because normally you'd be given U, A, T naught, right? You'd be given, and then temperature of the coolant. You'd be given everything you need to know. So you can plot this as a straight line. R of T is some constant slope times T minus some other constant that you can compute. So in some ways, the G of T line is more involved. And you can use Excel to do this. You know, you just pick a temperature, you can plot G of T versus T. So if you do that, you will be quite surprised to see, depending on the reaction order, you'll be quite surprised to see some really interesting things. So this is G of T, R of T. So when you plot this, it can look something like this. This is your G of T curve. It can look something like this, which is surprising, but that's what's going to happen. And it's gonna look even more, the higher the order, the more wild it's going to look really. The reason is because there are many XAs that can be solutions to the equation. That's really the reason. Now, if you plot your R of t, you're gonna get a straight line. This is your R of t. Now, the operating temperature or the operating temperature of your reactor is going to be where they intersect, because obviously the equation is G of t equals R of t. So this is gonna be your operating temperature. Okay. Any questions? All right, I think you guys got this. So yeah, so it's rather simple if you do it graphically, right? You plot your G of t curve, and then you plot your R of t, you find out where they intersect. However, there is this really interesting phenomenon that can happen. As I mentioned before, the G of t curve can have multiple solutions because of the way, mostly because of the order of the reaction, can have multiple solutions. And the first thing that can happen is the idea of multiple steady states. So what is multiple steady states is that literally that the reactor can operate at could operate at any of multiple steady states. So if you have your G of t and R of t curves, and your G of t curve kind of looks like this, which it can, let's say for a second order reaction or third order reaction, your G of t curve looks like this. And then when you solve your R of t curve for a certain temperature, inlet temperature, you get this. This is your R of t. So if this is your R of t curve, suddenly you have 3 points that solve your equation. All 3 points solve your equation. And these are 3 different XAs because you use XA to plot G of t. So these are 3 different XAs and also 3 different three different reactor temperatures. So the question can always be which one of those is the reactor going to operate at? Meaning, so now this is the idea of multiple steady states. It can be a dangerous phenomenon because keep in mind, this is temperature, right? You could have a 350 Kelvin here, right? And then over there is about 800 Kelvin. So, so there's a thought of, well, how much heat is the reaction generating depending on the temperature of the feed. So we're going to talk about 2 things. So multiple steady state is this phenomenon, but that can lead to a couple of things. So you can think of stability. So the first thought is reactor stability at a specific conversion. Okay, so we're gonna name the points 1, 2, and 3. So let's look at point 1. So the one thing to note is that if you increase T naught, if you increase T naught, your line is going to move. Okay, so this is increasing T naught. Or decreasing T naught is going to go the other way, because T naught is in the intercept, not in the slope. So if you go back up, if you look at that, if you increase T naught, this number becomes larger, more negative. So your line is moving to the right, as in, right? It's basically going to move to the right as you increase T naught. So let's say for example you increase T naught a little bit. So your question you're asking is point 1 stable? So is the reactor going to go back to point 1 if there's a fluctuation of the inlet temperature, for example? So if T naught fluctuates, what's going to happen? Now, the one way to look at this is to ask yourself, is point 1 going to be a stable point? Is the reactor going to go back to point 1 if there's a fluctuation in T naught? So that's the question. And the way to look at it is look at how much heat is generated versus how much heat is removed. So if T naught fluctuates, you'll find that R of T is larger than G of T. Basically, you can look at the slopes, right? So if R of T, which is heat removed, is larger than G of T, reactor will go back to point 1. Okay. Similarly, if the fluctuation is in the negative, as in if T naught goes down, the heat generated is higher than the heat removed, then it's going to go back to point 1 again. So you can say here that point 1 is stable. So any fluctuations, that steady state will remain that it will go back to that steady state from any fluctuation in temperature. It's the same thing with point 3, right? If you take point 3 and it fluctuates to the right, the amount of heat you're removing, if you look at how big that slope is higher than this one. So that means it's going to go back down. And similarly, the other way, the amount of heat you generate is higher than what's removed. So now let's look at point 2. Point 2 is where the instability exists, because the amount of heat that you're generating is higher than what's removed. So if T naught is moved and you are somehow at point 2 operating, your temperature of the reactor will increase and your conversion will increase until it hits point 1. So that's what's actually going to happen. So that's why we look at point 2 and say it's unstable. This is an unstable steady state. So any fluctuation in temperature will move it. If the fluctuation in temperature is increase in T naught, it's going to go up all the way until it reaches T1, point 1. But if the fluctuation is making T naught go, or RT go this way, it's going to actually go down to 0.3. So you can have a system where if you're operating at an unstable steady state, well, the idea is you won't be operating at an unstable steady state, but if you were to be at one temporarily, the reactor is going to adjust itself, either give you high conversion or low conversion, because this is your G of T curve. That's based on conversion. So this is the first phenomena that you encounter when you have CSTRs, is whether or not you have multiple steady states and which ones of those steady states are stable. This G of T curve is still rather simple looking, because they're all ones that are very complicated depending on the reaction order. You can have really messy things on your hands. So the other phenomena is reactor blowout. This is still graphically. We're showing all of this graphically because it's simpler to show and it's simpler to explain. So we can have the system called a phenomenon of reactor blowout. Basically, the reactor sort of stops producing. Instantly stops producing. So once again, if you have your G of T, R of T curve, and your G of T curve looks like this, and you have your R of T curve that is borderline touching, like tangential, as best as possible. Then you have 2 points. So once again, this is, I guess I forgot to mention, this is where XA equals 0, right? This is where there's no heat being generated. Right? This is the beginning of things. So if for any reason your T naught decreases, if your T naught goes, so we can do this. If T naught decreases, or if you partially lose a little bit of your cooling fails. Your cooling fails could mean that UA goes down or goes up, or temperature of the coolant goes up. So you can have many different ways that your cooling can fail. So if that happens, you can have a larger. This is also going to change the slope, but it's going to change the intercept as well. So it's going to look like slightly different. But if it's only T naught that decreases, suddenly what's going to happen is that your R of T curve is going to go this way. So, and then suddenly you're operating at 0 conversion only. You're not operating at 0.1 anymore. You're operating near 0.2. So this is essentially your reactor just stops working. So that is some of the second phenomenon that can happen. And there is an example in the book that sort of looks at this phenomenon with an example. But again, these are all based on, say, if the problem is given and you will always be, for example, graphing G of T versus R of T, graphing G of T and R of T and finding where they intersect. So that's really what the format the problem is going to take in all cases. So it will be your ability to understand whether or not a point is stable or unstable based on these multiple steady states, whether or not the point is barely touching the G of T curve, so it could actually lead to reactor blowout. But there is a third phenomenon. There's a third phenomenon called feed temperature hysteresis. So you have the third phenomenon called feed temp hysteresis. And that introduces the terms of ignition or extinction of your reaction. Let's see, give me a second here. All right. So let's say now that you have, or you have let's say you have, I'm going to put this really big. You have a phenomenon where, again, this is T, your G of T, R of T, and you have your curve looking like that, your G of T curve. Okay, let's say that you have a reactor. When you came in the morning, the reactor was operating, you're starting it up. Let's say you start it up and your temperature is, you're heating up your feed. So your feed was somewhere, that made your R of T curve look like that. So this is your R of T curve, and this is where you're operating at. So you basically starting up the reactor, there's no conversion. Okay, there's no conversion. So you heat up your feed a little bit, and you get to a second point where nothing is happening. There's a little bit of conversion, but it's not much. And you get to a third, you heat it up a little bit more, and you get to this curve. Now, your reactor is operating at point C, although it's touching here as well, because you're not producing a lot of heat, so you're still at point C. But you know from your curve that there is a tangential point right there. Okay, that's just something to keep in mind. And then let's say that you move it up to, let's say, point D, and now you have the issue of multiple steady states happening, but you're operating at point D because you're adding heat, so you can't suddenly jump towards the top. So you're still at the bottom, adding heat. Let's say now you were to get to point E. Oh, this is not looking very good. So you get to point E, and then it also goes to another point. So let's now start naming them. We'll call this point F. We'll call that G, H. Okay, and then suddenly, so it's your reactor will be at point E, right? Suddenly you increase your temperature enough, and you start operating now at point I, which is high conversion, high heat, and you can get to point J. Now imagine, so this is what we call the feed temperature hysteresis, meaning that you can have different values of the temperature depending on your where and how you're heating or cooling the feed. So let's say that in this first case, you start by heating up the feed from point A. As you heat it up, you get to point B, you get to point C, you get to point D, and you get to E, and then you go to I and J. Okay. Now let's say, for example, you were to be cooling the feed. If you're cooling the feed from point J, you would go down to I, to H, to G, and to H, and then to B and A. So you would not go through C, D, and E. So that's what we mean by hysteresis. So you could plot this just as a function of conversion. I'm going to put this here on the left. So this is conversion. This is 1. So this is XA. And and this is temperature. This is the temperature of the feed. Okay. This is feed temp. Okay. This is just the temperature of the reactor. Okay. This is not the same graph. All right. So you start from 0. So you have your point A, B, C, D, and point E. And after E, it jumps up. There's H, I, J. Now, when we go the other way, if we're cooling from J, we go from J, I, H, we go to point G, and now to point F. And instead of going to C, we jump down to B. So this is what is feed temperature hysteresis. So it's rather important to understand that, because instead of what you would do, rather than heating up your feed progressively and getting low conversion until you suddenly get high conversion, which could cause an explosion in your reactor, right? Because you might not be adjusting your heat exchanger to remove that heat that you're just going from E to I, right? Now, because remember, you're operating at steady state. So steady state removal of heat and steady state addition of heat. Right? Steady state increased temperature. Every time you increase temperature in your feed, you reach steady state, but you have to remove some heat. So it has to be matching up. So if you suddenly produce a lot of heat, the reactor could overheat. So you have to be able to remove it. So this is very important to do. Now, rather than, so the solution to this issue is, if you want to operate at point I, rather than taking your feed and heating it up and sending it to the reactor, one thing you can do is to heat up your feed in a heater separately to the temperature I, and then feed it to the reactor. So that would be one way to get around this problem. Because otherwise, if you keep sending your feed to the reactor, say you have a heater, and you have your reactor. So if your heater, if your feed is at, let's say 350 Kelvin, and then you're like, okay, I'm gonna heat it up to 360, and I'm sending it to the reactor. And then you say, oh, there's no conversion, so let's heat it up to 370. Send it to the reactor. That's to 380. So this is how we're walking through these points. But suddenly you get to 400 Kelvin, and it goes from no conversion to a lot of heat being generated because of high conversion. And that's problematic. So what you should do instead of that is to heat up your feed to the temperature that you want to operate at. So you heat it up to say 400 Kelvin, and now it's going to suddenly operate at I, right? Rather than going through this step, which is have some safety problems associated with that. Do you guys have any questions? Now, a couple of terms. There's a couple of terms to keep in mind. It's just sort of a so light off is the sudden increase in conversion. When the feed temperature is being increased. From say an initial value to a high value. So you call that a light off. So it's this sudden increase in conversion. And the temperature at which that happens is called a light off temperature. It's the feed temperature at which light off occurs. So I guess I meant to say light off. So my handwriting is not very good because I'm writing upright because I'm afraid that my computer is gonna decide to stop working. Okay, so essentially, if you can think of it as the feed temperature that gives you point E is in fact your light off temperature, right? Because if it moves ever so slightly to the right, it takes off. So that feed temperature that gives you that. So this curve does not have T naught on it, right? This is not T naught. Okay, this is not T naught. This is just the y-intercept. If you look at your equation, you could figure out what y-intercept is, but it doesn't matter. The x-intercept. So this is just the x-intercept. It doesn't matter. This is not T naught. Okay. This, however, here is your reactor temperature, right? So this is what the reactor temperature is. So this is how is not T naught. T naught is part of it, but that's not it. And similarly, you also have the extinction temperature. The extinction temperature is once again the feed temperature, not the reactor temperature, the feed temperature at which you suddenly lose conversion. Okay. It has some similarity to the blowout process, but if you think of it, it's kind of similar. So in this case, your extinction temperature would be the feed temperature that operates at point C. So because if it goes ever so slightly to the left of point C, it basically the reactor shuts down. It operates now at instead of point F, it operates at point C. So that's what I wanted to clarify here. Those extension temperature and the light off temperature are feed temperatures, not reactor temperatures. Okay, because these are the ones you can control. Okay. And any questions? If there is none, we'll take a break and we'll reconvene at 4. We'll take a good 10-minute break. Then we will talk about, we'll do an example. We'll actually do an example problem, which I think I have, I hope I have. We'll do an example problem that illustrates this. And then after that, we will talk about plug flow reactors with heat exchange. So we'll take a short break so you can ask questions if you have.
Professor Denard.
Mm-hmm.
I just had a quick question, like about the research.
All right, let's look at a sample example. I'm gonna try this again, see if it works, because I think that's why my microphone stopped working out. That must be the reason, but let's try this one more time. Okay. This example is example 8.8 in the book. So we're just gonna solve that problem. I meant to post the homework last night, but realized I left the book in my office. I didn't want to go back to get it, so I apologize. So I'm gonna try and do that tonight, which will be your last homework, which is hooray, we're done. Done with that. So yeah, the example 8.8 in the book, you know, in few words, is about a simple reaction where A plus B goes to some products that we don't know about, or we're not told what they are. Now, it says it's an ideal CSTR. It gives you an FA naught of 2,000 mole per hour and a volume of 10,000 liters. And it gives you a mole fraction of YA of 0.2. So it's 0.8 in terms, it's 80% B being fed. It says that the CP of the feed, so this is the combined A and B, there's an average CP for the feed, is 60 joules per mole. Okay, well, it says Celsius, but that's fine. And the delta H of reaction, which is independent of temperature, is minus 37 kilojoule per mole of A. And your inlet temperature is 50 degrees Celsius. Okay, that's what you're given. And you're asking a few questions. The first question is, why would the G of T curve go up and down? Now I will draw that out to the best of my abilities. So the G of T curve looks like this from the paper, from the book. You can say that, see, talking about best of my abilities. It's not really best of my abilities. So let's say the G of T curve looks like this, where it starts, it goes up and then it goes down. So, and it gives you some units. I guess this is megajoules. So I'll put a big M. This is megajoules per hour. And this is temperature. But I guess it's in Kelvin. And there's some numbers on the curve. And here is such at 0. Okay. Then we have a 300K, 350, 400, and 450. So if you have the answer, you can type it in the chat. Why is this going up and down? The answer is simpler than you think. Oh, wait. Was chat. It's not because it reached light off temp. So the answer to this is because this reaction has some reversibility to it. That's pretty much what it is. So there is some reversibility to the reaction, meaning that as you increase temperature, at some point your conversion is not going to keep going up; it's going to go down because equilibrium conversion is changing, is going down with temperature. So that's why this happens. Okay. So yeah, that's just like a little nugget in the problem. If you, and I think we're gonna have another. No, we're not gonna have another example of it, but yeah, that's why I chose this one. So the G of T curve can have many forms. We'll try your fourth exam. We'll have a take-home exam when you have to draw out the G of T curve, right? Because that's using Excel, so no Python included, so you can all do it, and that will be part of your take-home exam. At least one problem will be that. So, maybe I'll choose a form that is, a little bit more interesting, and then you'll see some really interesting behavior with it. But it's easy to plot it. Really, it's not that difficult. You just have to go through the steps. So yeah, so this reaction is reversible. It has some reversibility to it. That's why at some point the temperature goes down. So the second question is, what's the fractional conversion of XA? What is XA? So now you have to, what you need to do is to plot your R of T curve, right? So that's what the question is to plot your R of T curve. And the third question is also related. What is the temperature of at exit? So I'll call it at the exit. So both questions have to be answered at the same time because you're going to do it graphically. So the one thing you need to do is to plot your R of T curve. So it's really that simple in the end. I guess we're going to do it that way. So that's another way that to write R of T. I think we went ahead and made it into the straight line, but really it ended up being, they ended up writing it this way for their solutions, which I should have just changed. Okay, that's the R of T. And previously we had written it by factoring out T, but it's the same. Okay, so you can plug in some numbers here. You're given the heat transfer. Are you given that? Oh, you're supposed to have been given that. Yes, you're given some more things. Sorry. You're given an area of 1 meter squared for heat transfer, and you're also given heat transfer coefficient of 800 kilojoule per meter squared hour degree C. And you're also given the temperature of a coolant of 30 degrees C. Okay, so you're given these as well. Apologize. So that with that you can calculate your R of T curve, and if you plug everything in, and you put it in megajoules, you convert everything to megajoule per hour, right? Instead of kilojoule. So this is in kilojoule per meter squared. You can convert it to megajoule, which is 0.8. So you do that conversion, you get an R of T curve that's equal to 1.4 T minus 54. So this is in megajoule per hour. So you can plot that. So yeah, so you can see that it's rather straightforward. And if you plot it, I believe if I try to do it correctly, the R of T curve is going to look like this. So you can actually calculate your temperature of the urea effluent. And then this here you can use to calculate. So once you know this intercept, this is your FA naught XA. You can calculate XA. This is your FA naught XA delta H of reaction. So you can calculate XA from that. So it's rather straightforward. So you don't have to, it's not actually so bad, these sorts of examples.
How did you get that point on the graph?
Which one? This one?
Yeah. Yeah. that
Well,
one.
yeah, but you basically you're gonna use Excel and plot this R of T.
Okay.
And it's just gonna basically where it intersects is gonna be the
Oh,
point
okay.
that solves your problem.
Got it.
Yeah. And then you can get your temperature exit, and then you can also get your XA because G of T is FA naught XA times minus delta H of reaction. So you can solve for everything. Yeah, it's pretty cool. So, all that hoopla for really nothing major. So you can look at every CSTR. You can easily solve for the steady state. You can solve, in conclusion here, you can solve for which of the steady states is the reactor going to operate at. You can understand phenomena such as multiple steady states, right? You can figure out which one is going to be stable. So if you're thinking of quizzes, that's what's going to be asked. For example, is the point stable and why? You can look at whether or not, examples where the reactor goes from operating to nothing happening. So this is the phenomenon of reactor blowout. You can have the feed temperature hysteresis, where as you increase temperature of your feed, your conversion barely moves until it suddenly jumps from some low number to a high number, which is called essentially a light off. So it could explode your reactor because you're not removing enough heat at that particular conversion. Or if you cool down your reactor suddenly, as you cool down your reactor, you're going a different path than if you're heating it up. So you're looking at this graph here. This is called feed temperature hysteresis. So you're going through a different path as you heat up compared to when you cool down. So, so the ability to identify these, it only depends on the ability to graph G of T and R of T curves. And once again, the procedure to do so is right there. So this is how you do it. And keep in mind, so this is where you solve your mole balance. So always remember, when we're dealing with energy balances, we're not just looking at the energy balance, we're also looking at the mole balance. So you solve your mole balance right here, and then you go into your energy balance, which is G of T and R of T's. Okay, so that's the process. And I'm gonna give two problems this afternoon for homework after class. Then that pretty much are similar to this in some ways. This is quite easy, but unless you have to basically use Excel to draw the G of T curve, it's really not that much more complicated. Now, there are some phenomena that I did not go over, one of which could be your losing your heating coil, for example, your surface area somehow, something happening that it goes down. So that will change your R of T curve, not your G of T curve. Your G of T curve is going to stay the same. It will change your R of T curve where it could change the slope, it could change the intercept, it could change both. So based on this equation up here, this is where you'll be able to make this assessment. What is actually happening to your curve, and what could be what would be the consequence of that. Keep in mind something quite interesting here, that if you don't have heat exchange, suddenly you're back to your adiabatic temperature yeah, suddenly you're back to your adiabatic temperature equation, right? Where FA naught XA delta H of reaction is gonna be this T minus T naught. So it's suddenly you're back to your original. Okay. So you can see how if you can also use that curve and operate adiabatically. It's the same idea. Where now you just don't have any heat transfer from outside. So we can also have a question where you lose your heat transfer and then what happens to the curve. So those calculations are also on the cards. Okay. Yeah, that kind of concludes the heat effects with CSTRs. Once again, it's all algebraic. Now let's look at heat effects with a PFR with heat exchange. So we'll cover some of this today and then we'll go over it half of next class. And then from the middle of next lecture to the end of the course, we will discuss internal transport in catalysts. And that will be the last topic we'll cover. Okay, so now let's look at the last thing we are looking at in heat effects. And I will say this is from chapter 12 in Fogler. This is not from the book, because the book does something that is the same, but they overcomplicated it. It's not that complicated. Now, if you go and read section 8.7, yeah, do it for the sake of doing it and then see what happens. It's overly complicated. It's not supposed to be that complicated. So we will just bypass this one and then we'll replace it with something more fun that you can use Python to solve. No worries. We'll just do that. Now, the book calls it feed product heat exchange. The idea is that, so we're not talking about feed product heat exchange. We're just gonna have a heat exchanger with a coolant on a plug flow reactor, okay, or a packed bed reactor. We're not gonna say feed product heat exchange. What that means is you are taking the heat produced from your reaction and then circling it back to heat up your feed. See that's something that happens typically in catalytic reformers, in the oil industry, in refineries. But typically what happens, so the heat that you make, like you produce lots of methane, lots of propane and butane, you burn it and you use the heat to heat up your reactor. So heat becomes a reactant rather than just, leaving. So that's something that happens usually in the chemical industry and in the oil industry. So we're gonna talk about that because it includes lots of Z's and Z primes, super confusing. And the other reason we're not talking about it is because there are very few examples that either I can find or that exist at the level of undergraduate to solve problems that involve feed product heat exchange. So in my opinion, it was just a bad choice to put that in. So we will replace this with something that is more straightforward. We're looking at plug flow reactors with heat exchange. And this is Fogler chapter 12. If you have the book, you can go through that. If not, I think this is gonna be enough. And their website also does a pretty good job of covering some of those topics. Although they have different nomenclature variables, don't worry. If you get it, you just figure out how they get their stuff. All right, so let's start by doing a little schematic. So our schematic is gonna be a tubular reactor, cylindrical. So we're gonna have a cylindrical reactor and we're gonna solve the energy balance on a slice of that reactor. So this is your reactor and this is your inlet. Oh, this is your inlet. These are inlet conditions. And this is your outlet conditions. Okay, you have some conversion, some FI, some temperature. Now, if you look at that little slab, which is the volume or catalyst weight, right, plus delta V. So that little slab in the reactor. And we have a temperature in this slab, for example. There is a temperature of some coolant, right? This is delta V. There's some coolant that's on the outside, for example, that's going either in the direction of the flow or opposite to the flow. We'll get to that in a moment. And there's some heat being added or removed, where it's U delta A, right, times Tc minus T, or U small a, I'll explain what that is, Tc minus E times delta V. So U small a, well, small a is the heat exchange area per unit volume, right? Per unit volume. So for a cylinder, and the small a is area over volume, is pi dl over pi d squared L over 4, right? And that's equal to 4 over D. So that's just what that little small a is for a cylinder. Just, keeping in mind. That's why we can do that times volume. Right? Okay, so if we do an energy balance on that delta V, so we'll do an energy balance on delta V. That reminds you of the mole balance on that we did for a PFR. It's very similar. So here you have some enthalpy going in and enthalpy flow going out. So in that unit, in that little slab of volume. So what the energy balance is going to be delta Q, which is right there. Sorry, this is delta. So delta Q plus sum of FIHI at V minus sum of FIHI at V plus delta V. And that's equal to 0. So this is an energy balance on that delta V, right? There's no reaction term, right? It's just heat, right? So that's what you have. Now, if you substitute delta Q, okay, and divide by V, divide by delta V, and take the limit. So if you take that, what you get is U small a Tc minus T minus derivative equals 0. So that's pretty much this. If you take this derivative, you divide by delta V and take the limits, you just get minus, because it's minus this plus this. So it's minus ddv of the sum of FIHI. And then you replace delta Q with what it is right here. So now the one term we have to deal with is this term, but it's quite simple to actually expand on it, because this term, so we can actually take this term right here. Right, so it is equal to this plus this. And keeping in mind that dFi dV is Ri. So this is your mole balance right there. If you remember, this is your PFR mole balance. Works out really nicely. So this is your RI, and this term here, if CPIs are constant, is FI CPI dt dV, right? Because HI is CPI delta T, so DHI dV is CPI dt dV. So these are your two terms. So you can then go back to your original form. Now, another thing you can do here for this term, this is equal to mu I times minus RA. Right? That makes sense, right? So if you have minus RA is a positive term, for example, right? If you have A, if A is your reactant, and you multiply by the stoichiometric coefficient of any species. So that's what this is equal to. So now, if you were to now take this term and say this is summation of HI mu I times minus RA. So this is replacing the FI dV, right, with this. So then it's equal to, but not the sum actually, it's just equal to, where is it? This is equal to delta H of reaction times minus RA. Okay, so the final form of this is going to be dt dV times RA times delta H of reaction. I put the delta H naught for simplicity, minus UA TC minus T divided by sum of FI CPI. So that becomes your energy balance for PFR. Yeah. So the one thing to keep in mind, a couple of things. I use TC as a convention to say temperature of a coolant, but it could be temperature of a heating fluid. So that's just my convention. And the one thing that you can rewrite it as dt dV, this is, the first term is heat generated. The second term is heat removed. You can see it's very similar to the CSTR idea of heat generated from reaction, but generated is conventional, right? Could be heat, removed because of reaction if it's endothermic, okay? Or, heat added from a heating fluid. So it could be these types of things. So just keep that in mind. But the one thing to know is that there is a slight difference here. So for an exothermic reaction, so we'll do that. For an exothermic reaction, so RA is a negative term, right? So RA is some minus K something something. It's reactant. Delta H of reaction is also negative. So Q generated is positive. That's just in this reaction. The Q generated is positive, and then Q removed. Let's see what we have. Yep. So what you end up having is that so your generated term is higher than your cooling term. So temperature will increase down the reactor. So that is in taking with an exothermic reaction, right? The reaction will increase. Now, so you can ask yourself, well, if you remove too much heat from an exothermic reaction, the reaction is never going to start. So you have that going, right? So the heat that you're removing from the reactor cannot be so much that the reaction actually never starts. So you have to remove a certain amount of heat, but not all of it. And we'll, between now and next lecture, we'll go some examples that show how this works. Okay, so in any case, now that leaves us with what I would say a new differential equation for a packed bed reactor or for a plug flow reactor. For example, if this is a packed bed reactor, which have dT/dW, we'll call this R prime delta H of reaction. And here, however, it's going to be UA over density, the bulk density of your catalyst, for example, and Fi CPI. So yeah, we won't derive this, to be honest, but this is going to be a form of it if it's a packed bed reactor rather than a plug flow. Now, without knowing, all the, how do I say it? Without knowing all of the intricacies there, the question that you're all interested in, I'm sure, is how do you solve problems that involve a heat exchanger on a packed bed reactor? So really, that's what you're interested in knowing, right? So if you have a packed bed reactor with heat exchange, what do you do? And the answer to that is very, very simple. The answer is very, very simple. So let's look at solving a gas phase. One thing you have to be extremely happy with, I would say, is that now that you've gone through multiple reactions and having to plug equations into other equations, you don't need to do that anymore because these can only be solved with some MATLAB or Python. So all you need to learn how to do is to set up your problem. That's all you need to know how to do now, is to set up your problem. So if you have a gas phase reaction with heat exchange, so you have your energy balance. So these are the things you need. You need an energy balance. So this is dt dv. It's just a function that has xa in it or eta, right? Depends. Can have a temperature in it and it have a coolant temperature. So this is the function, right? It has xa or eta right there in your RA. It has temperature. It has a coolant temperature. So that's the function. Now, the second thing you need is your mole balance. And that's what we, in terms of, for example, fractional conversion, it's just this. You can write it in terms of flow. That's the same. And this is a function of xa, temperature, and pressure, for example. Let's say there is pressure. Let's say there is pressure drop. So you can put your pressure drop term. Okay, so that pretty much puts together everything you have. So let's say this is pressure drop. This is we'll put W's in parentheses here for consistency. Okay, let's say there's pressure drop. Then the pressure drop is some function H, which is terms of pressure, XA, For example, if the expansion factor is not 0 and temperature, right? Because it has your XA in there, because XA is the temperature, has temperature function. So XA and temperature. And then, yep.
That lowercase p, that's just p over p naught, right?
That's just P over P naught, exactly.
Okay,
Yeah.
thank you.
And then you have a fourth term, a fourth differential equation, which is your heat exchanger. And we'll go about what that is, but I can tell you what it looks like. So you have dTc over dV or dW is U times A times T minus Tc over some mass flow rate of your coolant times the heat transfer coefficient of your coolant. This is obtained by doing an energy balance on the coolant. And we'll look at that in a moment. It's quite simple. I mean, it's very much similar to doing an energy balance on the fluid, but there's no reaction. It's just heat being exchanged through the walls of a cylinder. Okay, so it's not that complicated to do. So if you think about this, this is what you need to know for any problem you want to solve with that have heat exchange with a packed bed reactor. If it's a gas phase, then you're dealing with, pressure drops and the likes. If you have a packed bed reactor, of course, your mole balance now, your XA has, or your flow has a volumetric flow rate change. So you need to take that into account when plugging things into your mole balance. So these are things we've done before. So that shouldn't be it's just can be a little bit of a nuisance, but it's not impossible. So, so it's very much straightforward, to solve problems. As long as you have those listed, right, you can plug those all in Python and it will give you a profile for all of these as they change along the reactor length. So it's possible, for example, that your coolant molar flow rate is so high. So let's check this out here. If the mass flow rate of your coolant, I keep saying molar, but if the mass flow of your coolant is very high, then your dTc dW is equal to 0. So that's a constant, right? You can see it algebraically. It actually works out. So if it's not, if it's changing, and then we may take a look at if it's changing. Okay, so we'll do one last thing, and then next time we'll recap and do an example. So now we're going to look at this term. This is the new thing that was thrown at us, and we'll just look at how it came about in a moment. But now if we have liquid phase, so here we looked at gas phase. How do you solve liquid phase things? If you have liquid phase, you still have your energy balance, right? And then you have your mole balance. You don't have pressure drop issues. And your mole balance doesn't have a pressure drop term in it, right? And you solve the heat exchanger. So you have three ordinary differential equations, whereas with a gas phase, you end up with 4. If you have pressure drop, you end up with 4. And of course, you have your algebraic relationships. How do you relate? If you solve things in terms of XA, what's your rate equation? All these things you can kind of write down one by one and plug them in. That's how you would solve the problems. So yeah, that makes it really cool. So now, the one term we introduced is the heat exchanger term. So that differential equation, the question is, how does it come about? So we can look at an energy balance on the heat exchanger fluid. So this is one last thing we're going to do before we adjourn. So we're gonna look at that last. So we'll look at a little cartoon where we have a reactor. And in the reactor, we have, say, FA naught and T naught. Okay. So now we have a shell. We have the shell, and in the shell, we have something going at, like, say, TC naught with M dot C. So this is, your heat exchanger fluid coming in on both sides, right? And then the same idea, we have a volume slice that we're gonna look at. The one thing in this class we are not dealing with is reaction in the heat exchange in the radial, heat transfer in the changes, gradients in the radial direction. So things are only going in the z-axis, if you think of it, going down this path. So one dimensional. We're not looking at changes. Every slab we take, we assume that it's the same amount of heat in each. So same way that we looked at the plug flow reactor, there's no flow, there's no reaction in the radial condition, in the radial direction. It's all going down the z direction. Same thing here. So we don't have to deal with partial differential equations, really. That's what it would do to us. It would be partial differential equations. So we can look at a co-current flow, right? So co-current flow heat exchange would look like this. So we look at a little slab. We're just looking at just a little slab that with co-current flow. Okay, so if we took that slab, this is V, and then this is V plus delta V. If we look at this, we have FA going at temperature T at one end, and FA going at temperature T at the other end. That's the reactor. Okay, and then for the heat exchanger fluid, we have mass flow rate coming in at some enthalpy, and then mass flow rate coming out at some enthalpy. So we can do the same thing, the energy balance, where we look at this at V minus mass flow rate times enthalpy of your heat exchanger fluid at V plus delta V, plus the heat that is added through this wall. This is your Q, delta Q, right? So you have flow of enthalpy and then heat exchange. And that heat is U, A, T minus T times delta V. So it's very similar to what we did before. That's that delta Q, that is heat being transferred. So this is the rate of heat added by conduction through the walls. So that's just conduction heat transfer here that we're dealing with. Okay, so it's the same thing if we divide by delta V, right? Divide by delta V and take the limits to 0, and we find that it's minus mass flow rate DHC dV plus this equals 0. Now DHC dV similar is CPC. We say it's constant. DTC dV. And yeah, I'll write it out, plus UA T minus TC equals 0, right? And now we can solve for DTC dV. And that's just UA T minus TC divided by that. So this is how you came to the energy balance on the heat exchanging fluid. And I hope that's the same thing I wrote up here. Yeah, that's right. Okay, yeah. That's how you came about. This is for co-current flow. Okay, this is for co-current flow because we said that we go in at a certain heat, with certain enthalpy, and then we go out with a certain enthalpy. So that's co-current. Now, without going through the derivation, countercurrent I think for your exam, just write this down, really. Counter current, you switch the signs. That's all it is. That's all it is. It's counter current, the signs are switched. And that comes from this term. Because the temperature, the flow is going the other way. So it's a sign switch. It just comes down to that. So let's just keep it that simple. So these are the two, this is counter current flow. Okay. So these are the differential equations that you would need to solve for any plug flow packed bed reactor with a heat exchanger attached to it. Yeah, once again, to recap, what do you need? You need energy balance, which we derived earlier, right there. This is your energy balance. Keeping in mind that, you see, that TC has its own differential equation, right? That's how it also changes. You need your mole balance that you've done before. You need, if you have pressure drop, you can plug that in for gas phase stuff. If you can also plug in your heat exchanger. And this is how you derive it using an energy balance on the heat exchanging fluid. This here, it becomes co-current. And if it's counter current, you change the signs. And this is pretty much how you plug everything in. This is how you go about solving it. It becomes rather simple, honestly. Now, I can graph in it's the last thing I'll do, really. I can graph, for example, as a function of volume or catalyst weight, right? The temperature of the coolant, if it's exothermic, right? So the temperature of the coolant is gonna start some TC naught, and it's gonna go up. Or, you know, if the mass flow rate is really, really high, it's just gonna stay constant, right? So you can have this issue. So the reactor, right? So we can already kind of think what the reactor is gonna look like, right? The reactor may look like this. The temperature in the reactor may look like this, where it goes up, then it cools down. Now, at the point where the temperature of your coolant is the same as the temperature of your reactor, you're likely not getting any more conversion, or very little. Right? There is no more heat exchange. So the reaction is essentially stopping, especially since it's already reacted most of its reactants. So that goes without saying. So, you know, you can imagine, we'll work on this again next class, because I imagine you might have gone through it too quickly, but we'll do 2 examples next class and we'll go through it. Once again, if this is for exothermic, for example. Okay. And then for an endothermic reaction, what you can have is, this is your coolant temperature. I guess I should have just put temperature. Here's what I'm gonna do. I'm gonna erase this so that we don't get confused in the long run. Next class, we'll go over it again. So your coolant temperature is gonna start here. It's just gonna go down because it's just giving heat to the reactor. So this is endothermic. So that's what you sort of expect your coolant to, you could expect your coolant to look like, but it could look differently over time. With different conditions, it could look differently. All right, well, that's it. Next class, we'll go over 2 examples of using, doing this. I'm gonna post the homework this evening. It's gonna be due on the last day of class. It may even, I may even extend it to, let's say, you know, 24th, 25th, depends if you have, time, if you don't have exams and other things like that that you need to prepare for. So it's not the biggest deal. So that's what we'll try and do. Yeah, we'll just put a few problems that at least one of them you're gonna have to use Python on. But on Thursday we'll go over these kinds of problems, and we'll show on Python how the different profiles of temperature and pressure and conversion, all of that changes. One thing we will not do, and that's because it's more of a painstaking endeavor than anything else, is having multiple reactions with heat effects. We will not do an example of it. So yeah, I'm not quite sure exactly what to do about that, but it's more of a painstaking effort than understanding, because I think, understanding single reactions is plenty to be able to do these sorts of problems. Multiple reactions, you just got to keep track of etas and where to plug them in and how to plug them in there, your energy balance. We may look at a problem. Now that I'm going to change my mind, I'll pick one problem and we'll look at it for the sake of completion, not really for the sake of being tested on. We'll just take a look at one of those. So that way you'll feel, I don't know, like you've learned something more, let's say. But it's not really, it's more painstaking than anything else. So are there any questions? Are you guys good to go?
I have a quick question.
Yes.
In the notes, you said that this was in chapter 12. Is
Yes.
this our Robert's book?
No, this is in chapter 12 of Fogler.
Okay.
Yeah, it's a different book. Now, would you guys like me to share that book, I guess, right? That could be good, right? Share that chapter, because I have the whole thing on PDF.
Sure.
Yeah, I'll share the chapter. That could help. Some of you that would like to study from the books, I think that would help you. If you care for that, I'll do that this evening. I think I'll be able to find it. If I can, the question is, I have it on Kindle. Can I save individual pages? We'll find out, but I'm gonna try. Yeah, I'm gonna try. Yeah, but also on the Fogler website, let me check for you really quick. They have slides. I think, let's see, what do we have? What do we have? Which slide is it? Yeah, lecture 20, chapter 11. Yeah, chapter 11, lecture 20 on the website. They have slides that pretty much go over the same thing I just did, because I more or less copied those slides, if I'm being honest. That's what I ended up doing. So yeah, you can also refer to that. I'll put a link. Let me just try and put a link to this in the announcements right now. You guys can also see it. Any other questions? Oh, you mean, at 4:30 somebody asked what rho B was. That's the bulk density of your catalyst. Yeah, that's just the density of the catalyst. Oh, am I wrong? No, maybe I'm wrong. So hold on. No, it's the density of your fluid. Sorry, I'll take that back. It's the density of your fluid, heat exchange fluid. Yeah, I apologize. Okay, if that's all there is, you guys have been great. I will see you on Thursday.